Okay, so we're going to talk about calculations with chemical formulas in this section. We have seen before how to do, the chemical formula. So CH2F2 really means C1. There's an invisible one there, right? C1H2F2. It contains 2 atoms of F, which is fluorine, 2 atoms of H, which is hydrogen, and 1 atom of C, which is carbon. But that's one molecule. Okay, so one molecule contains 2 atoms of fluorine. It actually looks like this. There's a C, there's an H bonded to that, there's another H bonded to that, and then there's 2 fluorines off the C. It looks like this. And so that tells me there's 1 carbon, 2 hydrogens, and 2 fluorines. But that's only one molecule. So 1 whole mole of this molecule, which we remember is a giant number, it's 6.02 times 10 to the 23rd molecules of that. We can say that because there's a 2 here, that it contains 2 moles of fluorine. Okay, so 1 mole of CH2F2 also contains 2 moles of hydrogen and 1 mole of carbon. And so we can use these relationships as conversion factors to go between the elements and the molecules. So when we are going between atoms and molecules, well, actually that should be facing the other way, this way, atoms and molecules, we're going to need to use these kind of relationships. All right, so 1 mole of that contains 2 moles of this, 1 molecule of this contains 2 atoms of that. You just need to kind of get that straight in your mind, and then you should be fine. I apologize, I already wrote in the times and the equals because I didn't realize they would just show up first, but they're there because we're going to need them. So let's go through this. If we have 1 mole of water molecules, and we all know that water is H2O, that means 2 atoms of hydrogen per molecule and 1 atom of oxygen per molecule. So if we have 1 mole of those, how many molecules do we have total? 1 mole of anything is 6.02 times 10 to the 23rd. So that's how many molecules we have. But how many oxygen atoms do I have? How many atoms of oxygen? Well, I know that there's 1 oxygen in every, 1 oxygen atom in every molecule. So I'm going to use that as a conversion factor. So I start with my 1 mole of water molecules because that's what I was given if I have 1 mole of water molecules. And then it says how many atoms of oxygen. So I'm trying to get to that. So I have to use this one first to convert into moles. From moles into molecules. This is Avogadro's number. Remember that from last chapter, Avogadro's number. But then we need the new conversion factor. 1 oxygen atom is equal to 1 water molecule. And that only works for H2O. It's not like that is true for everything, but it's true for water molecules. 1 O atom is in 1 molecule of H2O. So that gives us a chance to, we've canceled out the molecules here. We've canceled out the molecules here. Actually, the moles too here. And now we have just O atoms left. So this is our answer. We have 6.022 times 10 to the 23rd oxygen atoms, which makes sense because there's only 1 per molecule. So how many atoms of hydrogen do I have now? Well, I have 2 atoms per molecule, so I'm pretty much going to have twice that. So here's our conversion factor here. We start again with the 1 mole of water molecules, and we cancel out both moles and water molecules. Here, we're just canceling out molecules, right? The water molecules. And we're left with H atoms, and we have exactly double what we had before. Okay, so this is a new conversion factor that you will need to be able to do. 1 oxygen atom is in 1 water molecule, 2 hydrogen atoms are in 1 water molecule. And remember, there's just always an invisible 1 after any letter or formula, like element symbol in a formula that doesn't have a number after it. All right, this has a star at the bottom because this is important. We'll definitely need to know how to do this. So if I have 3.4 moles of water molecules, that's H2O again, how many hydrogen atoms do I have? So our plan is we're going to first find out how many molecules of water we have, and then we know there's 2 hydrogen atoms in every 1 molecule. So we start with our 3.4 moles because that's what we were given, 3.4 moles of water molecules. And we know that in 1 mole of water molecules, there are 6.02 times 10 to the 23rd, water molecules. So we're going to cancel out our moles of water molecules. And then in one molecule, there are 2 H atoms. So now we have 4.094 times 10 to the 24th hydrogen atoms in 3.4 moles of water. All right. So it's not so hard. You just have a new conversion factor that you need to do. But I think you guys got it. So formula mass is we talk about formula mass. It's also called molecular mass or molecular weight. It is you just add up the masses of the atoms in a single molecule. So calcium chloride, which is really not a molecule, it's a formula unit, has 1 calcium and 2 chlorines. So we're going to I should probably put on do not disturb. We're going to put in 1 atom of calcium and 2 atoms of chlorine, and we're just going to add those up. Here we go. Sorry, and we're just going to add those up. So we have 48.08 AMUs plus 2 atoms of chlorine. That's at 35.453. We're just getting those masses right off from the periodic table. If you remember, we learned that last chapter. And we're just going to add these up. Okay, so we have 1, this is the calcium one, and then we have 2, these are 2 of the chlorine ones, and so we end up with 110.99 AMUs. That's the mass of 1 molecule. Mass of 1 molecule, or formula unit, whatever you want to call it, of CaCl2. Okay, but that's not the mass of a whole mole. If you had a whole mole of that, that would be different. I mean, it would be the same number, but it would be in grams. So we'll get to that in a second. Okay. So here it says that the molar mass of a compound, which is what we call it molar mass because it's the mass of 1 mole of a compound. And we learned about the molar mass of an element in chapter 2, and we knew that we can get that off the periodic table, and we just add up, we just have the AMUs there. But it's the same thing for a compound. We just have to add them up. Okay, so the formula mass of 1 molecule, formula mass is for a molecule, right, of H2O. So we're going to add up 2 H's and 1 O, and we get 18.01 AMU. But now if we had a whole mole of molecules, it is the same exact calculation, but now it's in grams. Okay, and we use this as a conversion factor. We go 18.01 grams of water equals 1 mole of water. Okay, so that's how that works. 18.01 grams of H2O equals 1 mole of water. And so we can write that as a conversion factor and put them over each other and flip them around. So now we need to use this to count molecules. So if we had a number of grams of a substance, we can use the molar mass. This should have a times here too. We can use the molar mass here of a specific substance and then use Avogadro's number to convert to the number of molecules. Note that you cannot just go from grams straight to molecules. You have to go through the mole first. Okay, you must convert to moles before you can get from grams into molecules. So let's look at an example. How many oxygen atoms are in 14.8 grams of calcium carbonate? Now we know how to name calcium carbonate and what that's called. So our plan here is to go from grams to moles and then molecules. And once we're in molecules, we can go into atoms of oxygen. Okay, so grams into moles, we're going to use the molar mass, right? And then moles into molecules, we're going to use Avogadro's number. And then molecules into atoms, that's where we're going to use our new conversion factor, 3 O atoms in every 1 molecule of CaCO3. And I know that calcium carbonate is not actually a molecule, it's an ionic compound, but instead of saying formula unit, I don't want you to get confused. And we'll just, this, by the way, doesn't say 30, it says 3 oxygen atoms. So I'll underline the O so that you, well, okay, now that doesn't look any better. Whatever. Here's our plan. So we're going to start with our 14.8 grams of calcium carbonate because that's what we're given. We are using here the molar mass. This is directly off the periodic table. We added up 1 calcium plus 1 carbon plus 3 oxygen, and we got 100.089 grams. So our grams are going to cancel here. Now we have moles of calcium carbonate, and that cancels here because we're putting molecules. This is Avogadro's number again, Avogadro's number. And so I hope that's okay that I abbreviated AV. It's just too long to write out. 6.022 times 10 to the 23rd molecules in 1 mole. We knew that. Now we have our new conversion factor over here. 3 atoms of oxygen equals 1 molecule of CaCO3. So our molecules cancel. We're left with atoms of O. And here we have our answer. 2.67 times 10 to the 23rd. All right. So I think that's pretty simple. Just practice it. Make sure you do a lot of practice problems. Again, there's a star down here. Pay attention to those stars, okay? Not that you're not going to have to know everything, but you will definitely be using this a lot. So just be careful. Okay, so this is composition of compounds by mass percent. Sometimes we just have a percentage of elements, and we can get that out of instruments and things like that. But we can actually just calculate it if we know the chemical composition. When it becomes helpful is when we don't know the chemical composition of something and we actually work backwards. So then we can get the percent and then go back into the formula. And so I'll show you how to do that later. But first, let's learn what this is. This doesn't make any sense when it's just A over whole. Like it's just the formula for a percent, really. So this isn't really going to help you very much until we get into a real problem. But this is like the part, right? And this is the whole. We always do part over whole for percent and then times 100, right? And that gives us a percent of A. But notice that it's the mass. It is not the moles. You always have to use mass for this. Okay, so let's do a real problem. We'll just kind of show you an example here. All right, so we have N2O5, which by now you know how to name as dinitrogen pentoxide. So we have dinitrogen pentoxide. We know it's N2O5. We can calculate the molecular mass. That's the mass of 1 molecule, okay? And that would be, because we're adding up 2 N's, 2 of them, and 5 O's here, okay? So we're adding those up. We get 108.02 AMUs for 1 molecule of N2O5. This is, oops, go back. This is the whole. This is the whole thing. Right? The part that we're trying to do, they're asking us the percent of mass percent of nitrogen. So we're going to use this. This is the part. This is the nitrogen that we want, right? So let's put that in 28.02 here over 108.02. We just multiply by 100, 25.94. Pay attention to your rules of significant figures and make sure you report the proper number of significant figures for the molar masses that you are using or the molecular masses that you're using from that periodic table. Okay, so now let's do the same one with mass percent of oxygen. Okay, so now we're going to do the mass of just the oxygen over the mass of the whole thing again. So this time, this one's the part, and this one is still the whole. Okay, so let's put that in, and we get 74.06%. Now, recognize that all your percents, like for all the elements in your compound, have to add up to 100%. Otherwise, you did something wrong. So it's a good check. This one was 74%, and the last one was 26 about, and that's 100. So we know that we did it right. Okay. So let's calculate the percent oxygen in this formula. This is CH3CH2OH, which is ethanol or ethyl alcohol. I know that it looks a little bit funny. It's not written like C2H6O, but that's for various reasons that you will learn in organic chemistry. So let's just calculate the percent oxygen here. I want you to pause this video and try it yourself. And then when you come back, we'll show you how to do it and make sure you got it right. So pause now. Okay, now you're unpaused, and we're going to do the percent oxygen here. So first we have to add up the molecular mass of 1 molecule of the whole thing. So we add up 2 C's and 6 H's. These are C's, these are H's, and these are O's, okay? 2 C's, 6 H's, and only 1 O. We just count them. We just count them here. Oops, I went in too far. Okay, so our mass of just oxygen was the 16.00. So that's our part. Oops, part. and this one was our whole, because that's the whole molecule. Okay, so there you go. We have 34.72%. Again, watch those rules for significant figures, just so that you know what you're doing. All right, so now we're going to work backwards. So if a scientist knows the mass percent of an element, and you can get that out of an instrument, okay? And we might not know what the compound is, but we know how many elements are in it and which elements are which percentages. We can work backwards, okay? So we can determine its molecular formula. But before we can determine a molecular formula, we have to first determine an empirical formula. Now, ionic compounds are always determined by the charges on the ions, so we don't have to worry about those. We would know if we had an ionic compound what the ratio would be because of the charges. But how do we determine the formula for molecular compounds? As you recall, they can combine in many different ways, and they also can combine with the same elements in lots of ratios. So we have to calculate the empirical formula. Now you have to be careful with this because not every compound has a unique empirical formula. They're often the same, even though they're completely different molecules. Again, just to recap, because we did learn about this in the last chapter, an empirical formula is the simplest ratio. Like we always express ionic compounds in the empirical formula. Yeah, so we want to find that for the molecular compounds before we can get the actual molecular formula. So let's show you how to do this. There are certain steps that you need to take. So here is an example, and it makes a lot more sense than like this thing. Okay, so an empirical formula, you have 39.999% carbon, but that's by mass. We have like 6.7% hydrogen, and we have 53% oxygen. All right, so how do you find this ratio is the problem. So first step, assume you have 100 grams. 100 grams of the sample so that the percentages convert directly to grams. What this means is that if we had a 100 gram sample, I don't know why my pen is writing like that. This would be 39.999 grams of it would be carbon, just carbon by mass. And this would be 6.714 grams of just, here, I'll put carbon there. This would just be hydrogen by mass. And then 53.287 grams of oxygen by mass. So this makes this whole like assumption right there makes it very simple to do this. All right, so that's the first step. Assume that you have 100 grams of sample. So now that we have the grams, we find the moles of each element. Okay, you use the molar mass to convert the grams into moles. And then we convert them to ratios, and I'll show you how to do this. This doesn't really make a whole lot of sense right now. But we'll come back to this slide. Well, actually, it's like a long way back, but you can come back to the slide when you need this part down here, but we'll talk about it, and then you can come back and kind of look at that. That might help you later. But for now, let's go through this, okay? So in a 100 gram sample, as we determined, the grams are the same as what the percents were, okay? Now we're gonna convert each one of those to moles. So if we multiply by the molar mass, right, grams go on the bottom because we're trying to get into moles, we end up with 3.33 moles of carbon, 6.66 moles of hydrogen, and 3.33 moles of oxygen. Now we can't very well make C 3.33, H 6.66, and O 3.33. That doesn't work. So what we need to do is we need to divide by the lowest number in the ratio, which happens to be 3.33. Now we have two of them. Usually it's only one that ends up being like exactly, you know, the lowest. But if we divide each of these, you have to divide them all by the same number, divide them each by 3.33. Here's what you get. You get 1, 2, and 1. Well, that's much better. We can now put that into our C, H, and O. So we have C, we pretty much have C1, H2, O1. But remember, the ones are invisible, so we just don't write them. It's just CH2O. Okay, so that's how you determine an empirical formula. Let's do another one. This one only has nitrogen and oxygen in it, okay? And so we wanna pretend that we have a 100-gram sample of it, convert these to moles. Okay, so now we have our number of moles. So now we're gonna divide by the lowest again, divide by the lowest one, and we get 1 to 2.499, pretty much 1 to 2.5. You cannot usually round the 2.499, but you can round it if it's like within like less than 0.1, which this is like 0.001, so that's totally fine. But pretty much we have that. And so that's not going to help us. And dividing by the lowest again, which is 1, is not going to help us again. We're just going to keep getting the same number. So what we need to do now is multiply this by a factor that is going to give us whole numbers. So in this case, it's pretty much easy to just multiply by 2, because we can tell already with a 1 and a 2.5 that if we multiply each by 2, we're going to get whole numbers. So 1 times 2 is 2, and this is pretty much 5 because it was 4.998, and we don't even have that many significant figures, right? So 5. So our empirical formula is N2O5. Does that make sense? Because this was N, and this was O. All right. So this kind of summarizes our plans a little bit. I think the steps on the other slide were a little bit easier to follow since they don't go around in like a square, but it's okay. Use whichever slide you like. If you like it to be visual like this, or if you want to see it in step-by-step format, then go back to the other slide. But yeah, so that's what you do. What happens here is sometimes it doesn't make it very easy if it's like just 1 to 2.5, you know, like sometimes it's like really weird numbers. And so on that other slide that I told you to come back to that part, that has like some helpful things. Like if it ends in 0.33, then try multiplying by 3 and stuff like that. So then there's a 4 and there's like, yeah. So as long as you get a whole number, you should be fine. And it has to be, again, the empirical formula is always the lowest ratio, right? It must be the lowest ratio. So you can't just pick like any number to multiply back. You have to pretty much find the lowest one that you could possibly multiply by to get something that's not going to reduce any further. Okay, so now a molecular formula is where there are multiples of the empirical formula. Okay, and we've learned what a molecular formula is. We've been over what an empirical formula was last time. Here is an example again from chapter 1, I think, where they have the same empirical formula, but they have a different molecular formula, and they are totally different structures. Like they're totally like benzene's a liquid and acetylene's a gas. Like they're just very different compounds, but they both do have the same empirical formula. And so what we need this number here. If we multiply this one by 2, we get C2H2, and that gives us the molecular formula. And this one was multiplied by 6. So what we're looking for is we're trying to figure out how to get these numbers to multiply. And in order to get those numbers, you need the molar mass, and it must be given to you. You can't figure that out. So here's what you have to do. First, you compute or figure out the empirical formula weight. So that's the formula weight or the formula mass of the empirical formula you just figured out. Okay, you just figured out. We did CH2O. We would add up a C, 2 H's, and an O, right? Then we find the ratio. We put the whole molecular weight, the whole molar mass that you're given on the top. You will be given that in the problem, and you put your empirical formula weight that you just figured out on the bottom, and that gives us N, which was what our 2 and our 6 were. These are N. Okay, so that's supposed to be an arrow. Sorry, I'm like terrible at this. Okay, so then we just multiply by N and we get our molecular formula. So let's see an example. Here's our empirical formula, CH2O. We just figured that out. And we're given now that the molar mass or the molecular mass, whatever you want to call it, the molar mass is 180.1 grams per mole. Okay, so we know that the empirical formula is CH2O. So we need to add those up. So we need the formula mass here. Okay, you have to add those up, and now you have the molar mass. So first we add them up, we get 30.026 grams, and now we simply divide. The larger one goes on top because you always want to get a whole number. Okay, so this is This is different than the percentage one that we did where the bigger one goes in the bottom. This is the molar mass, the whole molar mass goes on top, and this is the empirical formula mass. Empirical formula mass that you just calculated. Okay, and when we do this, we get 6. So we had CH2O. So now we're going to multiply that by 6. We get C6, H12, O6. So that's how we do that. That's how we get a molecular formula from an empirical formula. So let's do this one. Benzene has an empirical formula of CH, and its molar mass is 78.1 grams. What is its molecular formula? Okay, so in this one, we didn't have to figure out the empirical formula first. It just gave it to us. And it gave us the molar mass. So it is molecular formula. First, we have to add this up and get the empirical formula mass, right? We have to add up 1C and 1H. And then we know we're going to divide 78.1 divided by whatever we get there. So let's see what this looks like. The empirical formula was 13.02 because we added a C plus 1H to get that. And then we divide 78.1 divided by 13.02 and we get 6. So we take our CH and we multiply that by 6 and we get C6H6. Okay, so that's how you figure out a molecular formula from an empirical formula.